Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And today we are going to continue our discussion about functions by stepping into transformations of functions. And what we have here is really a discussion about how to graph base graphs that have been shifted left, right, up or down. They've been stretched vertically, compressed vertically, or stretched horizontally, compressed horizontally, or reflected about an axis. So you have been exposed to this in the past, probably several times to be honest with you, but it's a good idea to kind of cover that material again, just in case that it's been a while. So let's go ahead and hop right into it. So graphing functions using vertical and horizontal shifts is what we're going to do in this specific video. In future videos, we'll do other types of manipulations or transformations. These two are called rigid transformations. And that's because really they're not compressing the function or stretching it or really bowing a function or anything like that. They're just literally moving left, right, up, down. They move that rigid object left, right, up, or down. Now, given this theorem, vertical shifts of a function. So given a function f of x, a new function, which we are going to call, and let me change I'll go ahead and highlight that right there. Let's see. So given a function f of x, a new function g of x, which is f of x, that original function, plus some constant that we're calling k, is a vertical shift of the function f of x. It lifts it up k units or down, or moves it down k units. So let's see here. All the output values are changed by k units. That's what I basically just said. If k is positive, it shifts up. K is negative, it shifts down. That should be actually a review. You should know that from your pre-req course. You should also know that for horizontal shifts, if I give you a function f of x, a new function g, which is equal to f of x minus h, where h is some constant, different letter there on purpose, honestly, is a horizontal shift of the function f. Now, this is what throws people off. If h is positive, the graph will shift right. If h is negative, the graph will shift left. But what throws people off is not that. It's because when you're working with a function, so let's just take a g of x right now. Let's take a look at this. And let's say I have an x minus 2 quantity squared. Well, by that theorem, it says it'll look just like a parabola. We know that the parabola just goes through 0, 0, and 1, 1. And it'll move it 2 units to the right. So 1, 2 units to the right, let's just say. And so in the end, we get this wonderful 1, 2 units to the right. Well, when I teach this without the minus h notation that you see right here, I tell students, because I usually teach it this way. How do I say this? I teach it this way where I say, f of x plus h. That's how I generally teach it. And I say it moves the opposite direction of h. Probably a better way of saying it is this. Whatever turns this argument right here, let me zoom into that. Whatever turns the argument of f, this guy right here, whatever turns that into 0, that's where the new vertex is, or that's where the new center of your function is. So in our case down here, we had an x squared, or a parabola, but now it's an x minus 2 squared. And what turns this argument into 0 is 2. So that's how far it's been shifted, 2 units. 2 plus 2 units, so 2 units to the right. Anything that happens on the inside of a function, and this is all the inside of the function right here, anything that happens to the inside of the function affects the graph horizontally. So it's going to move the graph 2 units to the right. Anything else I want to say about that? I don't think so. Not right now. Let's go ahead and hop forward and take an example. Now, I do want to say this. Normally, when you're doing transformations, whether they're shifts, reflections, stretches, or compressions, you do not use something like Desmos. You do everything by hand. However, this is a really good way to see what the effect of those H's and K's are by using something like Desmos. So I'm going to bring up Desmos here, and I'm going to go ahead and type in the function f of x, and we said it was going to be sine of x minus h, and that sine function, and that sine function, there we go, plus k. When you do this in Desmos, it asks you if you want to add a slider for each constant here, what we would call a parameter. I'm going to click all, so I add a slider for each of those, and I'm going to set them both to 0. That's the base value of it. A couple other things that you might or might not know about Desmos is that you can set the step size. So let's say that I want the h to vary from -5 to +5, and I want it to step by ones. You can totally do that. And you do that with the k value as well. So -5 to 5 step by 1. And so they only change by 1 unit each. Now here's our sine function, standard sine. You've seen that before. And we know that the k should adjust the output values, the y values. So if I increase k from 0 to 1, it should lift, and it does, lifts up the function 1 unit. Then we have 2 units up, then 3, then 4, then 5. So you could play with this all day long. Not that you'd want to, but there you go. And then the same thing. Notice it's sine of x minus h. So if h were 1, let's just pretend. I'm not going to plug that in yet. But if h were 1, it would shift the sine function over. Now, remember, you want to make that x minus h turn into 0. So it would shift, if h was 1, then it would shift over 1 unit, because 1 minus 1 would turn that into a 0. So if I let h be 1, you see it totally does. And actually, I think this one might be a little bit better if I don't step by 1, just for the visual. I'll step by 1/100th. And so now if I show you that it starts to, I increase h, you'll see this very smooth increase to the right of our function. By the way, the sine is, well, sinusoidal, and so it starts to repeat itself after a while. So there is a point where the sine will start repeating its pattern. And then you can combine these, right? So you can go down 2 units and then over to the left 1 unit or something like that, which I can't obviously target very well. All right, so that's how you could use Desmos to put in a couple parameters so you can see how this looks. I leave it to you to actually create your own function and to do the minus h and plus k thing, but I highly recommend that you play with this. And that brings us back to the page that we were just on, and there's really nothing else on that page. It just says go over to Desmos and fiddle around with that and see what they look like, right? And now we're to a new problem where it says here's a function g of x which equals the natural log of x plus 1/2 plus 1, and instead of using Desmos, graph this by hand. Now, this is a very traditional style problem, and I definitely think that you at this level, at the college algebra trigonometry level, that you should be able to graph this easily by hand. Now, the way that I would recommend doing it is to first graph the base function, and then after you're done graphing the base function, you want to graph the first translation, transformation, which would be y is equal to the natural log of x plus 1/2. Some people will ask, does it matter what order that I do this in? And it does. I'll go over that when we get into graphing multiple transformations at once, but I will say the way that I write my functions is as follows. I write them as some number times the function itself, in this case, the natural log, of bx plus c. So if there was some number on x, like a 3, it'd be 3x plus 5 or something like that. And then plus d. I write it in that order because if I write it in that order, I can just do my operations from left to right. And so you'll hear me repeat that throughout all the video lectures, but I'm just letting you know that that is how I tend to do things. It avoids any type of issues you might have with doing the wrong transformation first. After I'm done graphing the horizontal shift, I will then graph the vertical shift, which is, and it's, by the way, when I say I graph the vertical shift, I graph that vertical shift affecting the transformed function, which is transformed from the horizontal shift. So let's go ahead and do this. You should recall that the graph of the natural log does have an asymptote, because natural logs cannot have negative numbers in their arguments, nor can they have 0 as their argument. So there is a vertical asymptote for the natural log at x equals 0. This is the x-axis, and well, that's the y-axis. I just have it equaling 0 right now as far as x. So then you just quickly sketch out the natural logarithmic function. And I think what some people do is they have to plot points. Plotting points is like riding a bike with training wheels. You would never enter like a race, a bike race, a cycling race with training wheels on your bike. That is a rookie move, a rookie 3-year-old or 5-year-old move. Plotting points is gone. That should be well in the past. If you have to rely upon that, you need to really, really review your functions, your graphs of functions. Now, I do say here that I will still label points, but I did not graph this by plotting points. I just knew what the graph looked like. The points I'm going to label here are 1, 0, because that is on the natural logarithmic graph, and e, 1, because again, that's on the graph of the natural logarithm. If you don't know that, I will have a video in the future on graphing logarithms, but you should know that from your intermediate algebra course. So this is the graph of y is equal to the natural log of x. And now, so that's our first, I don't want to call it our first because actually I number steps later on. So that's our graph of our base function is what I would call that. And now we're going to graph the horizontally shifted version of it. Let me go ahead and draw XY axis in here. There's X, there's Y. Now, when you shift things horizontally, you're literally just grabbing that graph right there and you're moving it left or right so many units. And by the way, you're also moving the vertical asymptote. So look at the argument here. What forces that argument to become 0? When I say that argument, I should highlight it. This argument right here. The argument of the function is what we would call that. And what would cause that to be 0 is a negative 1/2. So everything's been shifted 1/2 units to the left. All the x values lose a 1/2, essentially is what I'm trying to say. So let's go ahead and see what the effect is of that on our graph. For example, x equals 0, the vertical asymptote, it gets shifted. You subtract a 1/2 from it, so it gets shifted left 1/2 units to x equals a negative 1/2. And I try to be somewhat accurate here. And then I just draw my natural log, knowing that these points are also shifted left by 1/2 unit. So I'm going to subtract a 1/2 from 1, 0 as far as the x values go. So this will be 1/2, 0. And then as far as the x values go, the point e, 1 will be shifted to the left 1/2 unit. And that's a little bit tough. I think a lot of people feel like intimidated by writing this, but you shouldn't. This is just e, and you lose another 1/2 off of it, and the output's 1. You can leave it like that. That's totally fine. And now I will go ahead and draw my natural logarithmic graph. Remember, the natural logarithm has a vertical asymptote, but not a horizontal asymptote. So it'll still climb forever and ever and ever. All right. So check and check. Let's take a look at the graph, the last piece, because we're almost there, right? We just want to graph the +1 version of that. So I'll take that graph and I'll move it up 1 unit. So here I go. One final panel is what I'd call it. So each of these are just called panels. There's the x-axis. There's the y-axis. My vertical asymptote, since I'm only moving the y values here up by 1, the vertical asymptote actually does not change. It stays at x equals a negative 1/2. What does change are these 2 points. I'm adding 1 to their y values because, again, we're about to graph y equals, natural log of x plus 1/2 and then plus 1. So the plus 1 is going to change all the y values, add 1 to them. So instead of going through 1/2 comma 0, it's going to go through 1/2 comma 1. I'll just park it right there. And instead of going through e minus 1/2 comma 1, it's going through e minus 1/2 comma 2. Some instructors are sticklers for labeling the axes properly and all that fun stuff. I am not. If you're in elementary algebra, yes. But by the time you're in this course, which is a college algebra / trig course, I know you know how to label an axis. So I'm not super concerned about that. What I'm more concerned about is the scale of things. And notice the scale of how I've labeled points kind of does work out, right? If this distance right here is a 1/2, then this distance is probably about 1. So that works out. So I'm just really trying to think of like, okay, does the scale kind of work out? Yeah, it does. So otherwise, I'm just going to graph my natural logarithmic function. There we go. That's literally all you have to do. Again, there's no horizontal asymptote, so that y value will grow without bound. When I say that y value, I mean that one right there. Just the right edge will continue to climb and climb. And I may have mentioned it in a previous video, but if I haven't, I'll just say it right now. Natural logs are one of the most important functions that you could ever encounter in mathematics. Okay, so let's see what's up next. By the way, you could probably see at the top of my screen, it says I have 18 pages, but that's only if I was to go through my entire lecture video here, and I'm not going to go through, or I'm sorry, my entire lecture for this section, and I'm not. This is actually the last page we're going through right here. So write a formula for the function graphed below. Now this, after what we have just gone through, it's very enticing to say this is the natural log, but it's not. And you might say, but how do you know it's not? Well, I know it's not because it doesn't continue to fall. If it continued to fall, then I know it's a natural logarithm. But as written, I totally know that that's a square root function. It's not a cube root because a cube root would do this. So it has to be a square root function. It could be a fourth root function or some silliness like that. But to be honest with you, right now we're just dealing with base functions. And you should recall there are 8 or 9 base functions that you should know. The base functions you should know, and I'm not going to graph them, but you should know how to graph y equals x squared, y equals, oops, that was supposed to be a y, but it's not, y equals x cubed. You should know how to graph their roots, so y equals the square root of x, y equals the cubed root of x. You should be able to graph reciprocals, y equals 1 over x, and y equals 1 over x squared. Right there you can see I have 7 functions, and I told you there's 8, possibly 9. The eighth is y equals the absolute value of x. Very, very popular function to deal with transformations. And depending on the author of your text, there's one more. I don't quite subscribe to this one being a base function, but y equals k. That's just a constant function, a horizontal line. So anyway, those are the 9 base graphs you should be strongly familiar with. If it was y equals the square root of x, well, the square root of x normally goes through 0, 0, and 1, 1. Now, I told you you should not be plotting points to graph these, but to be honest with you, it sometimes helps just to see what the graph looks like. So 0, 0, 1, 1, it goes through 4, 2 as well. And the question is, how do I get from that red curve to the blue curve? Well, you can see it's been lifted 1, 2 units, and it's been shifted to the right 1 unit. So 2 units up, 1 unit over. So if that's all that's happened to it, then I know that this graph right here, which I'm going to call f of x because I want to, is like the square root of x, except it's been shifted to the right 1 unit. Now you should be asking yourself, is that a plus or a minus 1 there? Well, if it's shifted to the right 1 unit, I would love it if when I plug in 1, this argument becomes 0. So that means that it's going to be an x minus 1 because, again, shifted to the right 1 unit means that your vertex, I guess, or your starting point for graphing is at x equals 1. And as I mentioned earlier, that means when you plug 1 into your argument, you want the entire argument to become 0. So that's why it's an x minus 1. A lot of other people, myself included, often just say, listen, if you're going to the right 1 unit, it's x the opposite of 1, right? So it's, if you went right 1 unit, it'd be minus 1, x minus 1. If you went left 1 unit, it'd be x plus 1. Anyhow. The other thing we know is we lifted 2 units, so I'm going to put a plus 2 on the outside. And that's it. It really is it. If you do that to these points, like this is the point 1, 1, and this is the point 0, 0, well then the y value gets lifted by 2 and the x value gets shifted by 1, so you're at 1, 2, which makes sense. And this point right here, the y value gets lifted by 2 and then the x value gets shifted by 1. So it should be, let's see, x value, add 1 to it, should be 2. Add 2 to the y value, it should be 3. Let's see if that's right. 2, 3. Yep. That is the function. That is totally the function. So again, all this video was about vertical and horizontal shifts. And because you've seen this before, I don't go into big details about it. I just kind of get it done. In the next video, we'll cover, let's see, I think we're doing reflections possibly in the next video. So I'll see you then.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.